It's my great pleasure to introduce Dinesh Manocha. Dinesh Manocha is currently a professor at the Computer Science and Electrical and Computer Engineering at the University of Maryland at College Park. He leads a major research group on geometric and simulation algorithms with applications to computer graphics, robotics, and virtual environments. He works on a very wide range of research topics, including graphics, robotics, and acoustics. Today, he'll be giving a talk on learning-based audio simulation.
Thank you for the introduction. Can you hear me?
Yes.
Okay, great. So thank you. It's really honor to be here. Actually, I'm right now in Japan attending a ARIS conference, a Conflictor 2 conferences, but it's an honor to speak to everybody about audio simulation. I have a lot of audio samples in my PowerPoint slides, and I just make sure that you hear them well on Zoom. So we've been hearing a lot of talks about, audio visual and audio simulation, audio components. I would primarily focus purely on the recent work on physically inspired machine learning for audio simulation, and hopefully they can be combined with audio visual. But I want to a little bit bring you up to date with a lot of research, which is more published in graphics and VR literature on how learning methods are used for different audio simulation. So this is some work I've been doing with a lot of my students who are named right here. They are my students at Maryland, also some collaboration in Peking University with Sheng Li. So the kind of application I'm looking at, if you look at all the devices we have where audio has played a big role, we see all kind of speech assistants like Alexa, Siri, and everybody knows that their performance depends on how far is the source of sound from the speaker. If it's very close, near field, it works well, but if the background noise or far field, the challenges come up. So we need to have better sound simulation understanding on how to make them work better. We heard many talks about localization sound. Many talks just before the break were on papers on that and event detection. And again, it really depends on how far is the event sound generator and where the microphone was. Same problem come up here. Then if you go to game engines, game engines, of course, is more like a direct problem. They want to generate realistic sounds to improve your sense of plausibility when you're playing a game. Gamers use an amazing amount of sound, but they still do a lot of artificially generated sound there. And of course, VR, especially with, you heard of, we talked some talks about before lunch about ambisonics. And if you hopefully get the latest Quest Pro, which just Meta announced last week, the amount of sound effects they do, spatial sound, it's a big chunk. So all these applications need either simulation of audio effects in the scene or simulation audio effects in the virtual scene and rendered to the user to make the experience quite effective. So sound simulation is a pretty old topic. It goes back to 60s, almost 60 years old. And we teach about a basic pipeline where you model the source. Source is every sound generates some kind of pressure wave. And whether it's a human vocal noise or whether it's a falling object or it's a river bubble, the all kind of pressure wave comes up. And you model different kind of source, different kind of absorption material. Then how sound propagates in the environment, which is called propagation. And eventually what device you have, your human ears, or you could have ambisonic speakers, or you could have laptop speakers, or you could have headphones, with spatial sound. All these issues come up. So if you want to do any kind of audio-based reasoning, it's good to have understanding of how these processes work. And what we are trying to do today is tell you new machine learning based approximation to really model the processes as accurately as we can. So just to give an example of what we do in physically based sound simulation, which has really in the last 15 years, you'll see a lot more papers in SIGGRAPH or interactive graphics or IEEE VR conferences or robotics and VR, AR and SIGGRAPH where we do. So there are two parts to it: generation of sound called sound synthesis and transmission of sound called sound propagation. So I play some audio samples and hopefully they come across okay on Zoom. So here's the generation of what's called modal sound when you strike this plate. Were you able to hear it? Can anybody type? Were you able to hear the sound or no? Great, thank you. And then this is just a generation of synthesis. How about we place this sound in a very big cathedral? How will the echoes come across? So you could hear a lot of reverberation because of this tall, the big height of the ceiling. You know, when the sound hits the ceiling and come back, the time reverberation can be between 1 or 2 seconds, and therefore you hear the echoes. And of course, the idea is that this is all virtual. This is virtual real. What if I could play this sound synthesis in the cathedral, how it would sound? This is where simulation comes with the picture for long tail. So this is what we have done. My own group has worked on this problem for about 12 years, and we developed physically based sound simulation methods. They're getting quite plausible. In fact, a lot of game engines have licensed up technology. You see them here. But you know, these methods are still quite slow, especially simulation and low frequency wave propagation is too slow for real-time applications. So what we have been working for the last 3-4 years is, can we bring the machine learning, a lot of work coming from computer vision and other literature, can you bring those networks and use them for sound simulation? And we call them what is called physically inspired learning. We will try to model it physically as faithfully as we can. So I'm going to talk about 4 parts of my work. I'll go over 4 sets of results. The first is called model sound synthesis. This is a pretty well understood topic in the last 2 decades in mostly in graphics and VR. You're given model analysis, and you can see how you take a mesh on the left, you generate a hexagonal model, and you perform this vibration modes, depending on how many modes you have as spherical harmonics, and you compute the mode shown by the color. And that generates a mode, and then you do the acoustic transfer radiation, and that's what generates the sound synthesis. This is a very mature area called modal sound synthesis, and you see lots of papers on this topic. Except if you look at these previous methods, you know, the number of modes can really grow up. It boils down to computing lots of higher RD decomposition, which can take many minutes to hours. So it's a very slow process, and depending on the object comes up here, but it's so. So what we have been proposing and working on over the last few years is basically can become neural network-based solution where we generate our training data, but have physically inspired network. And the good thing is they can handle arbitrary shapes. And nowadays, you know, people want to the sounds generate on even on your latest iPhone, your mobile phone. You have inferencing processors and do this in real time. So this is what we try to do, and I'll show you the results we have. This was presented at SIGGRAPH talk just earlier this summer at Vancouver. So I'll show you very briefly what a pipeline looks like. There are 2 parts to it, actually 3 parts to the mixed vibration solver, which is totally inspired by sparse matrix vector multiplication. We model this thing, a radiation solver, and then we perform acoustic transfer maps. So we show different learning networks for each one of them. I won't go into the detail of that. You can find them in a long paper which has all the details on that. But the idea is that in the classical literature, you're solving this, you know, sparse matrix vector solver for eigen decomposition, and you try to span a trial of space using eigenvectors. So we basically build a network which is totally inspired by this process and try to, you know, model that with the convolution quite well. This is what we call a physically inspired network using self-supervised learning using errors. And again, in the interest of time, I won't go details of that. But it's the kind of architecture you see. Basically, you do a 3D sparse net, do vertex to voxel, vertex to vertex, and then you can feed back to the Rayleigh-Ritz method. And then eventually they go into what is called LOBG. It's a basically sparse solver for optimization. And again, we want to combine that with it. So either there are 2 ways to do it. We do the network for this part, and this part we can still go back to classical because this is much faster, or we can model both these processes by network. We have tried both different options, some scientific and learning or some purely learning here. And then of course the radiation part, which is actually the most computational part of it, we propose an encoder-decoder network. Again, the details of that, the motivation of that, and how it works well, I'll just, you know, refer to the paper for lack of time, and you can see how this whole process works around there. So what do we have at the end? I'll pay you a whole bunch of examples. You'll see different kinds of model sounds, and we compare them by playing the physically generated sound, which is a ground truth, and then we play the learning-based method, hopefully to convince you how close they come. This is about a 1.5 minute, 2 minute video. You'll see about 7 different complex benchmarks. So they're both, as I said, mixed vibration solver as well as radiation solver here. and the numerical solver the ground truth here. So you see I'm playing different sounds. The first sound, the ground truth. The second one is a mix solver, third reduced solver. But you can see most of the time they're so sound similar, we call plausible, and therefore we get anywhere about 10 to 100 times speed up, but get an almost similar level of fidelity here. We also do user study to verify the plausibility here. So let me show more examples like that. So in this case, the object breaks down, and therefore real-time network performance helps a lot. This is a relation solver here. So look at the speed up. We're going from a few minutes to a fraction of a second here. Let me move forward in interest of time, but let me show you some very complex example. So this is using BEM, boundary element solver, which takes a long time, 28 minutes. And we are doing the same thing in a fraction of a second. Because real time, you can also edit objects. All this sounds in real time. Because real time, we can deformable objects too. And here's a very last complex object. So what learning has enabled us is, we can finally do very complex sound synthesis in real time. And of course, you do a lot of analysis, for the same running time, you compare the errors. If you compute more modes, and most of the time you can see the error is pretty small. So at least the benchmarks we did, and of course, we have a lot of unseen benchmark from training. It's very promising. So this gives a lot of confidence that at least we have good learning architecture for model sound synthesis. Let me move on to the second part, which is about the thing. And this is, again, you can see a lot of error analysis to really look at the modes and solver, which shows, the heat map, radiation solver, to show the accuracy is quite comparable. Now let me move to the second part of the talk, which is how sound transmits. And this is very important because all the devices and all the talks we heard this morning, whether it's speech, source separation, or ASR, speech recognition, or even speech localization, they all performance depends on how effectively is your system modeling the sound propagation in the room. So sound is basically when the sound is generated, how sound transmits, bounces off the walls, or diffracts around low frequency part.
Buck did not read the newspapers, or he would have known that trouble was brewing.
So that's the dry sound. And if you do the propagation, impulse response will sound like this.
Buck did not read the newspapers, or he would have known that trouble was brewing.
Hopefully you could hear the reverberation, it's on the web. Basically, that's where the challenge is this reverberation, while it enhances your experience in the VR, but for a lot of speech application, ASR or sound source separation, dry sound is the best case. The more reverberation you have, it degrades the performance of a lot of your speech system. So in a way, your speech training network, the accuracy depends on how well can it undo the defects of reverberation. So that's where the challenge of reverberation understanding comes in the context of speech application. We saw that. And literally what impulse response tells you is, there's three parts to the direct response, which is direct line of sight between the source and the listener, how early reflections, the sound bounces off, and how late order reflection. This could be up to hundreds of order reflections, especially we saw the reverberation in the cathedral. And there's a lot of work done. You can either do time domain analysis or frequency domain analysis, how this sound happens. So, and one of the things in propagation is how effectively can we model the RIR? Can we model the RIR in synthetic scene real time? But also, if I give you a recording of a sound signal, or which is part of an audio visual signal, if you just take the audio signal, how well can you record and analyze that? That's what it boils down to. So I'm going to show three kind of work we have done. One is the work one of my students, Jenu Tang, did just a couple of years ago, that if you're given a real world scene, like a recording, from the real world recording, can you figure the room parameters, what the reverberation, what the equalization? So we did one of the first inverse problem that from a recording, we figure out the room acoustic parameters, and then we can use those acoustic parameters to actually improve the performance of many speech application because we had the parameters from there. So the point here is, that ultimately you hear real world sound, you have a lot of microphones, but how do you really capture what is called the acoustic signature of an environment? How do you model that and how do you capture that? This is a very challenging problem here. So we basically have two parameters we chose. We said this is of course not sufficient, but good enough. What is the reverberation time and what's the equalization time? They're the two big parameters which is very effective with the performance of these systems and how can we recover them from a recording signal. So this is what we call scene-aware audio time. We propose a network called deep acoustic analysis. Again, I will not give the details of that, but the main idea is that based on a recorded signal, you extract these parameters, and then you can combine them with a geometric sound propagation engine to generate different sounds. So you could imagine if you're the giant speech signal, you could have figured out how it will sound like. So this is very important as you perform and develop next generation speech system based on these kinds of methods right here. Again, I will just show you very briefly what the network was. This is a couple of years old paper. I'm sure there are more networks available you could do. And we took a lot of impulse response available from databases like ACE Challenge and MITR. There are lots of them available. And we also took a clean and dry human speeches from different data sets and trained our network quite effectively. And this just shows the performance. There on the top are different benchmarks here. On the bottom time, you're seeing this impulse responses here. And this is the error, basically ground truth. This is the error in that RT60. You see 0.11 to 0.1. And the equalization is a decibel, this error and that. Of course, anything less than this small is quite good. So for these small real world scenes, we can do quite well. Now I'm going to show that we actually went and got recordings and did our own work to record and parameter simulate them, and you can see how well a job we do it here. So I'll play this video again. This is a minute-long video. It's a different audio qualities.
Infinitely many words can be written with a small set of letters. Infinitely many words can be written with a small set of letters. Infinitely many words can be written with a small set of letters. Infinitely many words can be written with a small set of letters. Infinitely many words can be written with a small set of letters.
So I played a different version, but I guess the ultimate challenge was the last two. That the ground truth of the recording was, the one before that was we extracted the RT60 and EQ from that, and these were generated basically using sound propagation. Once you have the acoustic parameters, you could generate that. So that means we were able to reproduce the acoustic signature and fed into a sound simulator to get this quite well. That was a promising part of this work there.
The appearance of the island when I came on deck next morning was altogether changed. The appearance of the island when I came on deck next morning was altogether changed. The appearance of the island when I came on deck next morning was altogether changed. The appearance of the island when I came on deck next morning was altogether changed.
I just saw Jim near the new archaeological museum. I just saw Jim near the new archaeological museum. I just saw Jim near the new archaeological museum. I just saw Jim near the new archaeological museum.
In language, infinitely many words can be written with a small set of letters. In language, infinitely many words can be written with a small set of letters.
So you could see a lot of comparisons, with different methods. Again, the best way to hear this, the videos on the website, download them, hear them with a headphone. That get much better appreciation than as opposed to listening on the speakers in the room and especially over Zoom. So one of the recent things we have done, given that we want to do more and more machine learning method, do we have large data sets? So there's been a lot of work on visual data sets. Computer vision is amazing for all kinds of data sets for recognition or action detection. There has been some work on more and more data sets coming up. There are databases for IRs and there are databases for acoustic event detection. But what we wanted was a very complex room impulse responses because we're looking at application like gaming or VR on one hand, plus also speech, because speech, your Alexa could be any kind of environment. So this is some work recently, there have been some data sets at least that came up, but they don't have too much diversity in terms of number of scenes, 2 to 11, something like that. There's also previous work on sound spaces and another version coming out sound spaces there, but that are also related to some very small related real world data sets. We want to go capture and generate very large synthetic data sets. So this is a paper again we presented at SIGGRAPH earlier this year. It's called GW dataset. We took at some real world scenes like 3D front, which is like about 19,000 rooms. And now you can also take ScanNet with real world scene. There's one thing is geometry. The one challenge is how do you get material properties? So in acoustics, the two kind of material property which makes the difference, the absorption coefficient and the scattering coefficient. And typically they're not available. Even if you capture with the cameras, you get the geometry, you get the visual color texture, but you don't get the acoustic property. So we came up with a scheme using some idea from NLP where we basically look at the characteristics or labels of the material and use that to assign. And finally, we use our own work on physically based simulation where high frequency is done by geometric ray tracing, low frequency done by wave, FTTD. And this is of course slow, but this was just offline. And we use a lot of public and open source data sets. So this is the whole pipeline. You take a complex model. This is one of the 19,000 model from 3D front. You look at the physical annotation, figure out this is a table with solid wood, assign the material, go to the material, run the simulator, and they generate that. So it's a pretty long, complex thing. Of course, this was synthetic pipeline, on a cloud, taking a long time. But the idea was to get a big data set like that. The one challenge was, how accurate our simulator is, because we're trying to simulate the impulse responses. And so we compare. Now, recently, the acoustic community has come up with what's called a benchmark. It came from Aachen University called Benchmark for Room Acoustic Simulation. There are different kinds of room where they actually recorded, real world recorded. And the challenge for simulator is how close can the simulator come to the recording? And we actually showed that if you do different kind of simulation, if you do geometric, which is only ray tracing, high frequency, but hybrid, which is ray plus wave, which is what we did, and measure. Of course, the real major sound has of ambient noise, which like here we can't model that, but at least you see that our hybrid is getting pretty close. For some peaks. The main thing is look at the peaks here, and our hybrid is pretty close, and that gives a sign of that our simulator, if you give it the right material properties and right shape, is getting pretty close to real world scene. Now remember the accuracy of IR will depend a lot on the speech application that you use them for. So how do we do them? What's the benefit we show? So literally, we have done a lot of work on even speech application, 3 version of that. This is, speech recognition here, and also speech reverberation. And we show that if we generate a synthetic data set, use it for training along with real data, we get quite a bit reduction in word error rate. So this shows that having larger data set, especially with hybrid simulation, increase the word error rate. And again, you can see we compare with the previous version of sound cases. Our synthetic data set, sound space is most real data set, small sample. Our geometric, only wave only, and hybrid. So this also shows here that if you have an accurate simulation combining low and high frequency part, this IR data sets give much better results in this thing. So this is literally using the knowledge of simulation data set effectively for improving the speech performance here. And that takes to the one last part of this whole work, that what do we do next? So more recently, we also presented what is called a real-time mesh to IR generator. That these IR generators, especially the frequency part, the low frequency part with BEM, can take many minutes to hours, depending on the shape. And can we, instead of computing numerically, can we also approximate that using a network? So this is an oral paper just presented just earlier this month in Lisbon. My student, intern Ratnaraja, presented that just 2 weeks ago in Lisbon in multimedia, where we take a mesh-based neural network. If you're given a mesh, can you compute the acoustic response? The good thing is once you're trained, and especially we use our GW database for training, as we go to new unseen part, this is really fast. Where previous taking minutes for low frequency, this is taking less than a millisecond. So suddenly, we can do real-time sound generation, propagation generation in real time. And this is a lot of application for speech application as well as many audio-visual talks that we heard this morning, what this can do. Now, one thing challenge happens is that when you look at real world simplification, geometry, the complex scenes are about tens of thousands of polygons. So in a machine learning, that leads to a very high dimensional latent vector, and dealing with high dimension data is always a challenge. So we use geometric simplification, which is a well-studied problem in computer graphics, because for acoustic part, we don't need very dense meshes. So we generate in simulation, it's a pre-process done once to literally reduce the dimensionality of latent space. And this again, the network. Again, I will not put the details of that. The paper has it. But this shows our whole mesh encoding network with the different vertex exposition and jam, and how do we go. So we use graph networks here quite effectively. GNNs work quite well here. And this is a full architecture, Ultimately, what you're given is, you're given the original mesh, simplified mesh. For sound simulation, you're given the source location as well as the receivers, where the microphone is and speakers are. You go to generator net, you do that, and finally discriminator net. So the overall network is a combination of generator network and discriminator network. And again, I will point you to the paper so you get the more detail. But let me show you, based on this, we have developed what is called the very first neural sound rendering system, which is real time with a very low computation overhead with a lot of training. But it's the first one, and we're playing in different kind of synthetic scenes. So again, you'll hear the sound and let you decide how plausible the sounds are, because this is where we want to really show that we can generate sound effects which are quite close to real world recordings. So this is one scenario, person inside the bedroom, the listener move around the house. So you'll see the sound shows a red sphere and how it sounds as you go around.
You make me happy when skies are gray. I hope you know, dear, how much I love you.
So this is purely generated on neural sound rendering. And if you go to our web page, you also see the physically based version. And hopefully it's so plausible that you probably won't hear the difference. So this is again just for gaming and VR. We now have a very low cost neural sound rendering, and they also love it because now you can even put this on your smartphone, because the runtime overhead is very, very small. Here's an example of a phone ringing in the bedroom, and you play the piano. So as you move around, there are two sound sources, and you can see how they mix together. The sources are fixed, the listener is moving around, you hear the sound effect change. One important thing in generating sound effects is the sound field is very smooth. So we have to make sure the neural sound rendering can preserve the smoothness, which is of course not easy to guarantee. But recently we also done some work. We're proposing a differentiable network, and there, some other idea comes up. There's a paper from Changwan's group recently on applying nerve ideas to the sound field. So a lot of new development we're seeing in nerve and other differentiability can also be applied here to further improve the network. So this is some more recent work we've done after the publication. And there's the last example of person speaking in the hall. So you can see like a speech application, and again, how this will help you.
In language, infinitely many words can be written with a small set of letters. In arithmetic, infinitely many numbers can be composed from just a few digits with the help of the symbol zero, the principle of position, and the concept of base. Pure systems with base 5 and 6 are said to be very rare, but base 20 occurs in English when we use score, as in 4 score and 7. Eventually, no system could keep pace with the decimal or Arabic number system, which has 10 numerals. The
So this
digits
example, you saw the locational sources, a machine playing a machine sound and the rope speaking. Human brain is still, very good at hearing what the speech was listening in spite of the machine noise. But if you bring your latest ASR device, right, especially if you move around with the background noise, your ASR device will really get confused. Now the challenge here is that you're giving two different sources, the machine playing background noise and the human speaking. You could separate them. So if we can do this kind of neural modeling of this environment, we can design much better speech system. So this is something we have done recently to show that this, of course, to show performance. The main thing is, simplification is the most time consuming, but it's only done once per model. But see, the encoder takes about order of few milliseconds, and the IR, this last part, this even takes a fraction of a millisecond. So this is the first system, which can generate very high, number of IRs, because we train on a highly accurate data set called GWA. So because the training on a very large GWA, it also gives us good guarantees of accuracy in this real world system. Now, just to show the benefit of speech, we just some more recent work we have done that as we generate that, because we're generating more, GWA was pre-computed IRs, but mesh to IR generates more runtime IRs along a path, and that can even further improve the speech system. So this is close to a case where you're getting more real-time IRs. Could you think of a self-supervised scheme? So this is where a lot of things are happening up there. So I think I'm running out of my time. 30 minutes have gone above my time. Sorry about that. Just to conclude, this is architecture, what's called neural IR generated in real time and neural rendering. So what I've given you overview, just this is purely an audio talk as compared to wonderful talks and audio visual you've seen the whole day. We are at a stage now, we have physically inspired learning methods for synthesis, propagation, and sound simulation. The goal here is now as we go ahead, as we see all these wonderful audiovisual methods, you can use these part of the network for the audio part. Whether the audio part is separate or not comes up there. But as you take these ideas and come at the audiovisual reasoning, it's possible that the accuracy of your audiovisual improve because these network-based solutions really model the physics, try to model the physics. So that there are benefits to that. And of course, we also generate our own physically accurate sound simulation called DWA. So I'll just stop here. I apologize for going a little bit over. If there's time for question or feedback, I'd like to hear from you. All these papers and all the videos are on the web page, and you're welcome to check them out on the web page. Thank you very much.
Questions?
Hey Dinesh, good talk. I have a question regarding the mesh IR and the mesh to IR papers. So like how easy is it to get the full mesh of an environment, and like if you can like work with noisy meshes, I mean how much noise can there be in the meshes?
So that's a great question. How accurate? So right now we tested it on like synthetic data set like 3D front. So that is a clean mesh. Now the question would see if you have a noisy mesh, how much accuracy do you want? Because if you look at a lot of data sets like, the Metaport, Replica, and you're seeing more and more zero databases coming up, people are coming up with real world capture seeing, and many times they don't even have a mesh. They may only just give you a scan or they give you a point cloud, So it doesn't even have to be a mesh. And some of the recent work we have done, we can even take the point cloud and scan. We are getting some results there. The challenge here is, the two kind of accuracy you want to evaluate. We haven't done full analysis there. One is that if you want to, in the acoustic community, if you had a real world recording with a nice microphone, you compare your IR with this. This is what I was doing here. The second thing is, the recording is for application like VR or AR. But if your goal is to really use that information for like speech analysis or acoustic events, how much accuracy you need. So for the second part, we have not done an analysis to know how much it is. But at least for the recording, we are seeing some decent matches, and I played a whole bunch of sounds to do that. So part of the answer is yes. Part of that, we still don't know yet how much accuracy is needed for speech or acoustic events. Hope that gives you an idea.
Great. I think there is also one question from Yapen in chat. He asks, for acoustic modeling and rendering whether non-speech and multi-source sounds introduce additional difficulties?
So this is a great question. First of all, in this simulation world, which I'm doing, it doesn't matter your source is human speech, music, or natural sound. So we don't do anything special for speech, although showing speech applications. But in terms of source, it could be any sound could be the source, any synthesized sound or any captured sound. Now, of course, multi-source sound. So, real world is very complex. In my previous work, we've done real world scene. Let's say if you go out down on a street, right? Real world is hundreds of sources come together. Let's say there are hundreds of cars, each making vibration noise. Or even if you go to the corridor of, let's say, I'm sure about the CBPR, exhibition was huge. There are thousands of people there, people talking. So definitely some environments have very complex, large number of sources, outdoor traffic or big crowded scenes. How much can we do? Right now, in the simulation process, we model each source individually. So if you got 1,000 people speaking in the background noise, are you going to model each one of them? We haven't done that kind of scaling then, but because the complexity will go linear with number of that, and again, depends on the application of how much fidelity you want. But at least we're testing on scene with a few sources, and we have no problem in getting good results there.
Great. Any more questions? If not, thank you so much for your talk.
Thank you. Thank you for giving me the chance. Appreciate it.